Welcome back. Let's look at this example. So here I'm taking H to be the subgroup of the integers, which is the set of all multiples of A. K is the set of all multiples of B, and D is the GCD of A and B, and G is the set of all multiples of D. And what I want to show is that G is equal to the inner product or the inner sum of H and K. So H and K are subgroups of Z, and G is also a subgroup of the set of integers. To see that, so basically we are claiming that DZ is equal to AZ plus BZ. This is the inner sum of AZ and BZ. And we want to show that this equality, and to show that, we basically have to show that DZ is a subset of AZ plus BZ, and AZ plus BZ is a subset of DZ. So this is what we have to establish, that to show that two sets are equal, we basically need to show that each one is a subset of the other. Okay, so let's first try to show that this statement, show that AZ plus BZ is a subset of DZ. To show that, I'm just going to take an element here and show that it's also here. So every element in this, on the left hand side here, is of the form AX plus BY for some integers X and Y. So let's note that for X, Y, and Z, we have AX plus BY. So I'm picking an element here, AX plus BY. And AX plus BY, now since D is the GCD of A and B, that means D divides A and D divides B. So then A is a multiple of D, so let's say A is DK. And similarly, B is a multiple of D, so B is DK prime for some K and K prime. And so now I can factor out the D here and write D times KX plus K prime. This should be an Y here instead of X. So K prime Y, and clearly then that's a multiple of D, so this is going to belong to DZ. And as a result, we see that every element of AZ plus BZ is also an element of DZ. So AZ plus BZ is a subset of DZ. Here I have a typo here. This should be NY. Okay, now let's show that DZ is a subset of AZ plus BZ. And to do that, we need help from the Euclidean algorithm. So applying the extended Euclidean algorithm, we know that the GCD D can be written as a linear combination of A and B. So D is AS plus BT for some S and T, for some integers S and T. Now, if we pick for any integer X, notice that DX, so that's going to be an element of DZ. So DX is equal to the following. So D, I'm replacing D by AS plus BT, and that's the same as ASX plus BTX. And then this is an element of AZ. This is an element of BZ. So we see that DX is in this set. So that means every element of DZ is in the set AZ plus BZ. So DZ is a subset of AZ plus BZ. So we have shown that DZ is a subset of AZ plus BZ, and AZ plus BZ is a subset of DZ. Therefore, they are equal. Here's a set of exercises. So in the first one, we are looking at the group of Z15 star. This is the multiplicative group of integers mod 15. And we are taking two subgroups of this group, H and K. You can check that they are subgroups of Z15 star. So here I want you to prove by checking explicitly that H inverse KH belongs to K for all H in H and K in K. and that's going to show that HK is a subgroup of this. And then I want you to compute all the elements of HK and then find out how the order of HK, that is how many elements are in HK. And also define L to be the subgroup of Z15 star generated by 7, and it is this. Then also list out the elements of HL, the inner product of H and L, and then see if it is the same as the entire group. The second one here, we have the G is a finite group and H and K are subgroups of G, and then we need to show that the number of number of elements of HK is the same as the number of elements of H times the number of elements of K divided by the number of elements of the intersection of H and K. Okay, so that's what we have to show in number 2. All right, and I have given a pretty good hint here to help you through this exercise. All right, so I'll stop here, and in the next video we will be looking at internal direct product.